Our future is written in the stars, but the pen is held by engineers. To become an interstellar species, we must solve 20 monumental puzzles that defy our current understanding of physics, biology, and technology. By the end of this journey, you will possess a complete blueprint of the obstacles we must conquer to leave our solar cradle forever. How do you build a ship that sails on sunlight, or create a tiny Earth that must survive for a century without a single leak? The answers lie ahead, revealing a path that transforms science fiction into undeniable fact. What does it truly mean for humanity to build a home among the infinite? That dream flickers in every culture's myths and legends, a silent pull toward the cosmos. Yet for millennia, it remained just that, a beautiful story told under starlight, because the universe is not built for beings like us. Our first tentative steps into space, from the beeping of Sputnik to the continuous hum of life aboard the International Space Station, did more than prove we could leave the planet. They held up a mirror, showing us in stark, unforgiving detail just how fragile and earth-bound our biology truly is. We learned that space is not simply an empty void to be crossed. It is a relentless environment that dismantles the human body atom by atom, weakens our bones, assaults our cells, and challenges our minds with profound isolation. This is the pivotal realization, the context that changes everything. We are no longer planning brief camping trips to the moon. We are architecting a permanent departure, designing arcs for voyages longer than a human lifetime, and building habitats on worlds that offer no air, no water, and no mercy. This shift from visitor to resident forces us to reimagine the very fundamentals of existence, energy, matter, and time. Every challenge we will discuss is a thread in this single, grand tapestry, the blueprint for a new chapter in human history. And to begin weaving that tapestry, we must start with the most fundamental barrier of all, the one that defines every journey, the tyranny of distance and the engine we need to overcome it. Distance is the first and greatest wall we must scale. Our nearest stellar neighbor, Proxima Centauri, lies over 4 light-years away, a journey of 40 trillion kilometers. With today's fastest rockets, that trip would take tens of thousands of years, longer than all of recorded human history. This makes the dream of interstellar travel not just difficult, but fundamentally meaningless unless we can drastically reshape our relationship with speed. We must stop thinking in terms of miles per hour and start thinking in terms of a fraction of the universe's ultimate speed limit, the speed of light. To make the voyage to another star within a human lifetime, we need to achieve what physicists call relativistic speeds, traveling at a significant percentage of light's velocity. This is not an incremental upgrade, it is a complete reinvention of propulsion. Chemical rockets, the workhorses that took us to the moon, are utterly inadequate for this task, their fiery plumes representing a type of engine that simply cannot carry enough fuel to reach such velocities. The quest for relativistic travel pushes us toward realms of physics that sound like science fiction. One promising path is nuclear fusion propulsion, where the same reactions that power the sun are harnessed in a compact reactor to heat a propellant to unimaginable temperatures, ejecting it at a fraction of light speed. The challenge is containing a miniature star within a magnetic bottle small and stable enough to fit on a spacecraft. Another, even more potent idea is the antimatter engine. When matter meets its antimatter opposite, they annihilate in a 100% efficient conversion to energy, the most powerful reaction known to physics. But antimatter is fiendishly difficult to produce in meaningful quantities, and even more difficult to store, as it violently reacts with any normal container. Then there is the elegant concept of the light sail, a vast, ultra-thin mirror pushed not by expelled fuel, but by the pure pressure of light itself from a gargantuan laser array stationed in orbit. Imagine a sail the size of a city, propelled by a beam of light concentrated from an installation larger than any structure we have ever built. The energy requirements for any of these systems are almost beyond comprehension, demanding power sources that could rival the output of small nations. And the engineering tolerances are unforgiving. A single microscopic flaw in a light sail or a magnetic containment field could mean catastrophic failure in the void. Solving this first challenge is about more than building a faster engine. It is about constructing a key that unlocks the cage of our solar system. But that key is useless if the vessel it propels cannot protect its most precious cargo, the fragile, living beings inside. For once you achieve these incredible speeds, you face a new and invisible danger, a rain of cosmic debris moving at a relative velocity that turns dust into a devastating weapon. Achieving relativistic speeds would be a triumph of physics, but it creates a paradox of protection. At such velocities, even a speck of interstellar dust, no larger than a grain of sand, carries the kinetic energy of a high explosive shell. Your vessel's forward shield becomes the most critical component of the entire ship, a sacrificial armor designed to vaporize incoming particles in a controlled flash before they can puncture the hull. Engineers are exploring ideas like a multi-layered shield of thin, spaced materials, or even a cloud of plasma projected ahead of the ship to act as a buffer. Yet this armor adds immense mass, which in turn demands even more powerful engines, a vicious cycle of engineering trade-offs. Surviving the journey, however, is only the first half of the equation. You must also ensure the crew inside not only survives but thrives for the entire multi-generational voyage. This brings us to our second monumental challenge, the creation of a closed-loop life support system that must operate flawlessly for decades, perhaps even centuries. Think of it not as a machine but as a living, breathing world in miniature. Every molecule of water, every breath of air, and every nutrient must be endlessly recycled with near-perfect efficiency. This sealed bubble of Earth-like environment, hurtling through the void, is called a closed ecological life support system. Unlike the International Space Station, which relies on regular shipments of air, water, and food from Earth, an interstellar ark has no supply line. It is utterly alone. The engineering splits into two interconnected realms, the physico-chemical and the biological. Advanced machines will scrub carbon dioxide from the air, extract pure water from humidity and waste, and maintain precise atmospheric pressure. But machines wear out and require spare parts. This is where biology becomes the ultimate engineer. The system must integrate plants, algae, and microbes not just to produce food, but to form the core recycling engine of the entire habitat. These organisms would process complex organic waste, regenerate breathable oxygen, and help purify water in a sustainable cycle. The profound difficulty is not in starting this miniature biosphere, but in maintaining its delicate balance for a human lifetime or longer. On Earth, vast ecosystems have buffers and redundancies we take for granted. In a sealed metal can, a single microbial imbalance, a crop blight, or a gradual buildup of a toxic chemical could cascade into system failure. Imagine a vital food crop succumbing to a fungus, or the carefully curated community of bacteria in the water recyclers shifting unexpectedly. The engineering challenge is about achieving unprecedented long-term stability, creating a system resilient enough to withstand internal fluctuations and external shocks without any possibility of outside help. It is about designing a world so robust and self-correcting that it can operate for a century without a single critical leak in its ecological logic. This tiny, engineered Earth must be a paradise of balance, because within it lies the continuity of an entire human community, whose well-being depends on every leaf, every microbe, and every drop of water. And to safeguard that community for the long voyage ahead, we must confront a challenge that strikes at the very core of human biology: the silent, invisible damage wrought by the space environment itself. Even within the sanctuary of a perfectly balanced biosphere, a more insidious threat permeates every corner of the ship, an invisible rain that no physical wall can completely stop. Space is not empty, it is filled with radiation, a torrent of high-energy particles from distant supernova and our own sun. On Earth, we are sheltered by a thick atmosphere and a powerful magnetic field that deflects this cosmic barrage. But beyond that protective bubble, every member of a crew is exposed to a continuous, low-level assault of galactic cosmic rays, punctuated by occasional violent storms of solar protons. These are not like the X-rays you get at a dentist's office. They are atomic nuclei stripped of their electrons, traveling at nearly the speed of light. When they slam into the delicate machinery of human DNA, they do not just cause damage, they cause chaotic, complex breaks that our cells struggle to repair. The long-term risks are sobering: significantly increased chances of cancers, potential damage to the central nervous system leading to cognitive decline, and harm to vital organs like the heart. This makes radiation shielding not just an engineering problem, but a fundamental biological imperative for any long-duration mission. The most straightforward solution is also the most burdensome: passive shielding. Surround the living quarters with a thick blanket of mass, something like water, polyethylene plastic, or even the ship's own waste and fuel reserves. It is a simple principle, using atoms to block atoms. But mass is the enemy of motion in space. Every extra ton of shielding requires exponentially more energy to accelerate to interstellar speeds, creating a punishing trade-off between safety and feasibility. This has driven scientists toward a more elegant, science fiction-sounding concept: active shielding. Imagine recreating a miniature version of Earth's magnetic field around your spacecraft. By generating a powerful magnetic or electrostatic field, you could deflect charged particles away from the hull, much like a force field. The promise is tremendous: a strong protective bubble without the crippling mass penalty. The reality, however, is a labyrinth of engineering hurdles. Generating a field strong enough to deflect high-energy cosmic rays would require superconducting magnets of unprecedented scale and stability, operating in the deep cold of space and drawing enormous amounts of power from the ship's already strained reactors. A single fault in this system could leave the crew catastrophically exposed. The ultimate solution will likely be a hybrid, a clever integration of multiple approaches. Perhaps the ship's structure itself is designed as a shield, with water-filled walls and hibernation pods placed at the core of the vessel for maximum protection during solar storms. Maybe fuel tanks are strategically positioned to absorb radiation, serving a dual purpose. This challenge forces us to think in layers, to weave protection into the very fabric of the ship's design. It is a constant calculation, balancing the weight of safety against the fuel needed to carry it, all to preserve the fragile genetic code of the explorers within. And preserving that code for the entirety of a voyage that could span multiple human lifetimes introduces an even more profound question, one that challenges our very concept of a crew. But radiation is only one facet of a deeper, more pervasive truth. Our bodies are exquisitely tuned for the specific conditions of Earth. Remove the steady pull of gravity, and the entire symphony of human physiology begins to fall out of tune. On a voyage lasting years, this dissonance could become a quiet catastrophe, arriving at a new world with a crew too weakened to step onto its soil. In the microgravity of space, bones lose calcium, becoming brittle. Muscles waste away from disuse no matter how much an astronaut exercises, and bodily fluids, no longer pulled downward, shift toward the head, creating a constant stuffy feeling and placing long-term pressure on eyes and the brain. The immune system itself seems to grow confused and less effective. These are not temporary inconveniences, they are a fundamental unmaking of the human form, engineered by millions of years of planetary life. To counter this, the spacecraft itself may need to become a surrogate for Earth's most constant force. The classic science fiction solution is rotation, using centrifugal force to simulate gravity. Imagine a vast spinning ring or a tether connecting two sections of the ship, whirling through the void. Within that rotating habitat, the outward push would feel exactly like standing on a planet. Yet the engineering is deceptively complex. To avoid disorienting Coriolis effects, where moving your head makes fluid swirl in your inner ear, the ring must be large with a radius measured in hundreds of meters and spin at just the right speed. Building such a massive, precisely balanced structure that can withstand the stresses of acceleration and potential impacts is a feat of structural engineering on a scale we have never attempted. But even with artificial gravity addressing the physical decay, another, more subtle threat remains: the mind in a metal box, confinement, isolation, and the crushing monotony of a starfield that barely changes for years could erode the crew's psychological resilience as surely as microgravity erodes bone. Here, engineering expands into the realms of architecture, sociology, and neuroscience. We must design not just a ship, but a society and a sensory experience. Advanced virtual reality could offer mental escape, not just as entertainment, but as a vital tool for psychological health, simulating walks in forests, visits with loved ones light years away, or complex training scenarios. The social architecture of the crew itself becomes a critical system, requiring careful selection, conflict resolution protocols, and perhaps even designed communal spaces that foster connection and purpose. And for the longest voyages, we may need to consider the most radical countermeasure of all, bypassing the psychological challenge entirely by placing the crew into a state of controlled metabolic stasis, a form of deep, medically induced hibernation that pauses biological and psychological time for the bulk of the journey. This fourth challenge is ultimately about integration, weaving together biomechanics, psychology, and structural engineering to create a vessel that sustains the whole human being, body and mind. It ensures that when the long voyage ends, the pioneers who step out are not broken refugees, but capable, sane colonists ready for the next, even greater test, transforming an utterly alien and hostile landscape into something they can call home. Stepping onto an alien world is a triumph, but the celebration ends the moment the airlock seals behind you. You are not a visitor on a guided tour. You are a pioneer in a land that offers nothing you can immediately use. The soil is toxic powder, the air is vacuum or poison, and the only water is locked in frozen deposits deep underground. This stark reality births the fifth great challenge, the art of cosmic alchemy, known as in situ resource utilization. It is the practice of turning the barren stuff of another world into the very foundations of survival and growth. Think of it not as mining, but as building a civilization from scratch, using only the raw materials you find at your feet. The first and most precious resource is water. On Mars, it exists as ice mixed with soil in the polar caps and possibly in subsurface glaciers. On the Moon, it hides in permanently shadowed craters at the poles. Your robotic prospectors, sent ahead or deployed upon arrival, must locate these deposits, then excavate them in environments of extreme cold, where temperatures can plunge hundreds of degrees below zero. The mined icy regolith isn't just for drinking, it is the keystone of a new economy. Through a process called electrolysis, powerful machines will zap that water with electricity, splitting it into its core components, oxygen and hydrogen. The oxygen fills habitats and spacesuits, becoming breathable air. The hydrogen, combined with more oxygen, becomes rocket fuel, allowing for the return journey or trips to other sites. Suddenly, the distant outpost is no longer a dead end. It is a potential gas station for the solar system. But a habitat needs more than air and fuel. It needs physical structure. This is where the soil itself, the endless, abrasive dust, becomes a resource. Engineers are experimenting with using concentrated sunlight or microwaves to sinter lunar or Martian soil, fusing the dust grains together into solid, ceramic-like blocks without needing water or cement from Earth. Other concepts involve using the soil as a radiation shielding blanket, piling it over inflatable habitats for protection. Perhaps one day, giant three-dimensional printers will use this processed regolith to print entire landing pads, roads, and building walls layer by layer. The true test of this cosmic alchemy is not the chemistry which we understand, but the machinery that performs it. These systems must be the most robust, autonomous factories ever built. They will operate for years in a gritty, freezing vacuum, choked by fine dust that gets into every moving part, with no mechanic available for a repair. They must be compact enough to fit on a lander, yet scalable to industrial output. Every drill head, every chemical processor, every robotic arm must be designed with a level of fault tolerance and self-diagnosis that makes our current Mars rovers look like simple toys. This challenge transforms engineers into universal providers, creating technology that can walk onto any rocky body and whisper to the stones, teaching them how to become a home. It is the ultimate expression of human ingenuity, proving that we can not only reach new worlds, but convince them to sustain us. And once we have the raw materials for shelter, we face the next logical, monumental task, constructing those shelters into something that can withstand an environment that wants nothing more than to tear them apart. A habitat is a promise made of steel and ingenuity, a bubble of Earth-like pressure holding back an alien sky that wants nothing more than to crush it into silence. Constructing these permanent homes is our sixth great challenge, a task that transforms architecture into a form of high-stakes life support. The first structures on the Moon or Mars will bear little resemblance to earthly houses. They will be multi-layered pressure vessels, engineered like deep-sea submarines, but designed to keep a precious internal atmosphere in, rather than a crushing external pressure out. Every square inch of their surface is a battlefront against a trifecta of threats: the relentless vacuum that seeks any microscopic leak, temperature swings that can span hundreds of degrees between sunlight and shadow, and the ever-present hail of radiation. This demands a complete rethinking of how we build. We cannot simply ship bricks and mortar from Earth. The cost would be astronomical. Instead, we must become architectural alchemists, using the very soil beneath our boots. One of the most promising techniques is large-scale, three-dimensional printing, where robotic arms layer processed local regolith, fused by concentrated sunlight or a binding agent to create thick, solid walls. These walls do more than define a room. They become integral radiation shields and thermal mass, slowly absorbing heat during the day and releasing it during the frigid night. Another approach uses compact, lightweight inflatable modules made from advanced fabrics, launched from Earth and then expanded on site. Once inflated, these structures could be buried under a thick layer of loose regolith, turning the planet's own soil into a protective blanket against cosmic rays and micrometeorites. But the engineering goes far beyond the shell. These habitats must be perfectly airtight ecosystems. Every seam, every window, every port for cables and pipes is a potential failure point. The internal environment requires a symphony of machines working in unison, sophisticated air scrubbers to remove carbon dioxide, humidity controllers to prevent condensation, and complex thermal regulation systems to maintain a steady, comfortable temperature despite the wild swings outside. Perhaps most importantly, we must design not for a single mission, but for a legacy. These first habitats are the seeds of a colony. Their design must allow for expansion, with standardized ports and connections so that new modules can be added, creating interconnected networks of living quarters, laboratories, and greenhouses. This architectural philosophy blends the brute force durability of aerospace engineering with the foresight of urban planning, all to create safe havens in landscapes that offer no forgiveness. And to keep every light on, every air scrubber humming, and every 3D printer building the next wall, these havens will demand a constant torrential flow of power, a resource that is nowhere to be found on the silent, sun-bathed plains. Power is the lifeblood of a colony, and on an alien world, the veins run dry. Every breath of manufactured air, every drop of purified water, every layer of 3D printed wall demands a torrent of reliable energy, a constant flow that must be generated in places where the simplest earthly solutions fail. This is the seventh monumental challenge, generating sustainable and massive power off-world. On Mars, for instance, the sun's light is only about 40% as strong as on Earth, and global dust storms can blot it out for months. On the Moon, the night lasts for 2 Earth weeks, plunging temperatures to depths colder than Pluto. Solar panels alone cannot shoulder the burden of a growing settlement. They become intermittent, dust-choked relics during a long, dark night. To truly become independent, we must look beyond the sun to the power within the atom. The most immediate and practical answer lies in advanced nuclear fission. Imagine a reactor, not the sprawling complex of a terrestrial power plant, but a compact, self-contained unit, small enough to fit on a lander. It would use a core of highly enriched uranium to generate heat, which is then converted into electricity through rugged, solid-state systems with no moving parts. The engineering miracle here is not the fission itself, but the packaging, creating a system that is inherently safe, able to shut itself down automatically in any emergency, and durable enough to operate flawlessly for a decade or more without any human maintenance. It must be a black box of power deployed by robotic missions long before the first colonists arrive, humming to life to prepare their new home. Yet fission, for all its promise, still relies on finite fuel and generates long-lived waste. The ultimate prize, the clean, abundant engine of the stars themselves, is nuclear fusion. Mastering compact fusion reactors would be a revolution, turning the hydrogen harvested from local water ice into a virtually limitless power source. The challenge is containing a star, stabilizing a plasma hotter than the sun's core within magnetic fields of unimaginable precision, all inside a machine that must be shipped across space. Whether through fission's gritty practicality or fusion's stellar promise, the power system becomes the colony's silent, beating heart. Its failure is not an option, for without it, every other system falls silent, the lights go out, the air grows stale, and the machines that make food from dust and ice go still. This dependency makes power the non-negotiable foundation, the first resource we must secure to make all other survival possible, including the most human need of all, a sustainable source of nourishment far from Earth's fertile soil. A thriving colony needs more than power and shelter. It needs a steady, reliable harvest grown under an alien sky. The eighth great challenge forces us to become master farmers of the void, creating sustainable food production systems that must feed generations without a single shipment from Earth. This is not about packing freeze-dried meals. It is about engineering entire miniature ecosystems inside pressurized domes or underground caverns, where every leaf, every root, and every nutrient cycle is meticulously designed and controlled. We must move far beyond simple hydroponics, where plants grow in water, to a holistic approach called a bioregenerative life support system. In this closed loop, plants do more than provide calories. They are the lungs and kidneys of the habitat, absorbing carbon dioxide from the crew, producing oxygen, and helping purify water through transpiration. The crops themselves cannot be ordinary varieties. They will likely be genetically optimized for our new worlds, engineered for shorter growth cycles, higher nutritional density, and the ability to thrive under the specific light spectra provided by efficient LED arrays, all while occupying the minimum possible space. Imagine dwarf wheat strains that produce abundant grain from a compact stalk, or tomatoes biofortified with extra vitamins. But a diet of only plants lacks complete proteins and variety, which is vital for long-term health and morale. This is where food technology becomes frontier science. To produce animal protein without the immense resource cost of raising livestock, colonies may rely on cultured meat bioreactors. These are not farms, but clean laboratories where animal cells are nurtured in nutrient-rich solutions, growing into muscle tissue for consumption without ever being part of a living creature. It is a profound reimagining of meat production. Another efficient protein source could come from insect farms, where species like mealworms or crickets, which convert feed to protein with stunning efficiency, are processed into flour or protein bars. The psychological acceptance of such a diet is its own engineering puzzle, requiring careful integration of flavors and familiar textures. The true test of this agricultural engine is its resilience. In a sealed environment, a single mold spore or a fast-replicating pest could wipe out an entire crop, threatening the colony's survival. These systems must be designed with robotic precision and sterile protocols, monitored by artificial intelligence that can detect the slightest sign of blight or nutrient imbalance. Automation will handle the planting, tending, and harvesting, as human labor is too precious to spend entirely on farming. And every part of the system must connect. Plant waste becomes feedstock for insects or compost, inedible biomass is processed for nutrient recycling, and even human waste, after thorough treatment, can provide vital nutrients for the soil. The goal is a symphony of biology and machinery, a perpetual motion machine of nourishment that transforms sunlight, carbon dioxide, and recycled elements into a nutritious, varied, and psychologically comforting menu. It is the ultimate test of our ability to recreate not just the mechanics, but the soul of a living world, ensuring that a community light years from home never knows the true meaning of hunger. Yet, to keep this symphony playing for centuries, we must solve a challenge that strikes at the very continuity of the community itself, the profound social and genetic puzzle of a population cut off from all of humanity. A colony's survival is measured not by what it consumes, but by what it reclaims. In the sealed environment of a distant world, there is no garbage day, no landfill, no way to throw anything. Every single output from the community, from a discarded food wrapper to the most basic human biological processes, must be captured, broken down, and transformed back into a vital input. This is the 9th monumental challenge, creating a near-perfect closed-loop recycling system that treats all waste as a precious resource. It is the ultimate test of our commitment to a circular economy, where nothing is truly wasted, only repurposed. The engineering splits into distinct streams, each with its own technological puzzle. The most immediate is human waste. Advanced sanitation systems, far beyond simple incineration, will use processes like pyrolysis, heating material in the absence of oxygen to break it down. This doesn't just sanitize, it transforms. Solid waste can be converted into sterile, carbon-rich biochar, a substance that can improve soil structure in the agricultural domes or be processed further. The water recovered is subjected to multi-stage purification, using a combination of filtration, biological processes, and advanced oxidation to render it perfectly clean, ready to re-enter the drinking water supply or be split into hydrogen and oxygen. Even the gases released are captured, with nitrogen and other volatiles carefully separated and returned to the habitat's atmosphere, but the waste stream doesn't end there. Consider the inedible parts of plants from the farms, worn-out clothing, broken tools, and packaging materials. Industrial recycling on Earth often involves sorting and melting, but a distant colony needs something more comprehensive. Gasification units could take mixed solid waste, applying intense heat and controlled amounts of oxygen to produce a synthetic gas, a mix of hydrogen and carbon monoxide. This syngas is a versatile building block. It can be burned for immediate energy, used as a feedstock for manufacturing plastics or other chemicals, or even fed into biological reactors to grow protein. Metals from discarded equipment are recovered through chemical leaching or electrolysis, ready to be reforged by three-dimensional printers into new parts. The goal is staggering: to approach 100% recycling efficiency for every consumable. This demands a cascade of interconnected machines, each performing a specific transformation, all overseen by an artificial intelligence that monitors the chemical balance of the entire colony. A failure in one processor, a clog in a filter, or a toxic buildup in a reactor could disrupt the entire life support chain. The machines themselves must be designed for ultimate longevity, with self-cleaning mechanisms and redundant components, because on Mars or a moon of Jupiter, you cannot order a replacement filter from a warehouse. This challenge reframes our entire relationship with material things. It forces us to design every object from the beginning with its end in mind, to see a water bottle not as a single-use item, but as a temporary vessel in a perpetual cycle of hydrogen and oxygen. By mastering this alchemy of renewal, a colony transcends mere subsistence and builds the foundation for true permanence, a society that lives within its means because it has learned there is no other choice. A perfect recycling loop is a colony's circulatory system, but it cannot build the bones of a new civilization. For that, we need hands that never tire, eyes that see in dust storms, and minds that can work alone for years in absolute silence. The 10th challenge is the creation of a robotic workforce, an army of autonomous machines that act as our scouts, our builders, and our tireless maintainers long before the first human sets foot on the new world. These are not the remote-controlled rovers we send to Mars today, which move with agonizing slowness and wait hours for instructions from Earth. For a true settlement, that delay is fatal. The robots must be truly intelligent, capable of perceiving a chaotic, alien landscape, making complex decisions on their own, and executing delicate physical tasks without a human in the loop. Imagine a fleet of robotic excavators landing on the moon. Using onboard sensors and artificial intelligence, they survey the site, identify the best deposits of water ice, and begin a coordinated mining operation, all while navigating treacherous terrain and adjusting their plan if a drill encounters unexpected bedrock. Back at the fledgling base, other robots would be the constant caretakers. One might perform a meticulous external inspection of a habitat module, its computer vision scanning for micrometeorite damage, while another, with dexterous manipulators, cleans solar panels clogged with fine dust or replaces a faulty valve in a life support system. In the agricultural domes, robotic tenders could monitor plant health, harvest ripe produce, and manage nutrient flows, all guided by an artificial intelligence that understands the fragile balance of the ecosystem. The engineering hurdles here are immense, spanning hardware, software, and the brutal environment itself. These machines need bodies forged from advanced composites and alloys that can withstand extreme temperature swings, resist abrasive dust that grinds like liquid sandpaper, and operate in a vacuum where lubrication is a constant battle. Their artificial minds require a new kind of intelligence, not just the pattern recognition of current artificial intelligence, but a form of machine reasoning that can handle the unknown unknowns. A robot sent to repair a leaking pipe must be able to assess the damage, understand if it has the right tools and parts in its inventory, and improvise a fix if the standard procedure fails, all without calling home for help. This level of autonomy demands unprecedented robustness in software and a deep integration of perception, planning, and physical action. It is about building partners, not just tools, entities that can be trusted with the literal groundwork of our future. Their success ensures that when human colonists finally arrive, they are not greeted by a silent, barren outpost, but by a functioning home, its lights already on, its fields already green, and its infrastructure waiting to be expanded. This constant growth, however, will demand a torrent of raw materials, pushing our robotic miners to delve deeper and our manufacturing systems to become ever more inventive, forging the future from the dust of an ancient, silent world. The thread that connects a scattered interstellar civilization will not be one of sound, but of silent light. Our 11th great challenge is to weave a web across the void, a network for communication and navigation that must operate with perfect autonomy for centuries. When colonies are separated by light years, a simple question sent to Earth could take decades to receive a reply, making real-time conversation and centralized control impossible. Each outpost, each ship becomes an island in a dark ocean, and we must give them lighthouses and a way to send messages in bottles that travel at the universe's ultimate speed. The solution lies in reimagining our infrastructure as a decentralized, self-healing nervous system for humanity. One promising concept is a chain of powerful laser communication relays positioned at strategic points in the interstellar medium. These stations would act as signal boosters, catching faint laser beams from one star system and amplifying them to shoot toward the next, creating a kind of optical telegraph line spanning the gulf between stars. The engineering demands are staggering. Each relay must be a marvel of longevity, powered by nuclear sources and equipped with self-repairing systems to maintain its precise alignment for hundreds of years without a single technician's touch. An even more elegant idea harnesses a natural phenomenon of Einstein's universe, gravitational lensing. Just as a glass lens bends light, the immense gravity of a star bends and focuses the light from objects behind it. We could position a spacecraft at the focal point of our sun's gravitational lens, turning our entire star into a natural telescope of unimaginable power. From that vantage, it could receive and transmit incredibly faint signals from similar stations orbiting other stars, creating a galactic internet with natural celestial routers. But sending a message is useless if it cannot find its intended recipient. This is where navigation becomes an art of cosmic wayfinding. Without constant updates from Earth, a starship must know its own place in the galaxy. The solution may lie in the universe's most reliable natural clocks, pulsars. These rapidly spinning neutron stars emit beams of radiation with metronomic regularity, each with its own unique pulse signature. By triangulating its position against a map of these celestial lighthouses, a ship's autonomous navigation computer could pinpoint its location anywhere in the galaxy to within a few kilometers, a feat of dead reckoning on a galactic scale. The computers running these systems face their own profound test. They must be error-correcting, self-diagnosing, and resilient to cosmic radiation that can flip a single crucial bit in their memory, potentially sending a colony's entire archive of knowledge into corruption. The data packets traveling this network will carry more than personal messages. They will contain the genetic libraries of Earth's biosphere, the schematics for new technologies, and the collective cultural memory of our species. This challenge is about preserving the continuity of human knowledge itself, ensuring that a discovery made on a world orbiting Proxima Centauri can become a gift to those orbiting Tau Ceti, and that no colony is ever truly alone in the dark. It is the engineering of shared consciousness across light years, a testament that even when separated by impossible distances, we choose to remain a single civilization. And to protect that civilization from threats we cannot yet conceive, we must look beyond the limits of our own biology to the creation of new forms of intelligence that can guard our future. Our galactic network would carry more than data. It would carry the very blueprint of life from Earth, a responsibility that introduces a profound new layer to our engineering mission. The 12th challenge forces us to confront a silent passenger we have carried on every voyage, the trillions of microbes that call the human body home. As we step onto new worlds, we risk becoming agents of a quiet, biological invasion, potentially smothering any fragile, nascent alien life with our own microscopic stowaways, or forever confusing the geological and biological record. This is the dual imperative of planetary protection, a field where engineering meets profound ethical stewardship. The first task is creating spacecraft and spacesuits of a cleanliness we have never before achieved. This goes far beyond simple sterilization. It demands designing entire systems that can be baked at searing temperatures or bathed in harsh chemicals to eliminate every last resilient spore, all without damaging the sensitive electronics within. Imagine a lander assembled in a facility cleaner than any operating room, its components treated like priceless artifacts being prepared for a journey into a pristine museum. The suits astronauts wear on the surface must be their own biological containment units, with multiple layers of isolation and airlocks designed to prevent even a single grain of alien dust from entering the habitat without first passing through a decontamination arch that scans for hitchhiking microbes. But what if, despite our best efforts, we discover we are not alone? The second task is to protect ourselves, designing quarantine and detection facilities of a sensitivity that borders on science fiction. A returning sample or a crew member would enter a multi-chambered isolation module, a biological fortress where robotic arms perform all analyses. The sensors within would need to detect life not as we know it, seeking signatures of metabolism or molecular complexity that do not rely on the DNA-based template universal to Earth. This is engineering for the unknown, building a trap for a ghost whose shape we cannot guess. These technical hurdles, however, are only the preamble to a much larger ethical question that our engineers must help answer. How do we settle a new world responsibly? Do we embark on the millennia-long project of terraforming, using colossal machines to thicken an atmosphere and melt ice caps, a process that would irrevocably alter or erase any native history the planet holds? Or do we commit to living permanently in sealed, non-intrusive habitats, treating the entire alien landscape as a protected wilderness preserve? There is no purely technical answer. This challenge demands that we build ethical frameworks directly into our engineering specifications, creating tools for settlement that are, by design, reversible, minimal, and respectful. It means designing mining robots that leave the smallest possible footprint, or atmospheric processors that can be dialed back or dismantled if we discover something sacred in the soil. It is the recognition that the ultimate measure of our success as an interstellar species may not be the grandeur of our cities, but the wisdom with which we tread upon new shores, preserving the story of the cosmos even as we add our own chapter to it. This wisdom must extend to the very minds we trust to build and guard these new worlds, pushing us to create partners in intelligence that operate beyond the limits of human biology and perception. The integrity of every structure we build in the void depends on the silent strength of its substance. Our 13th great challenge is to reinvent the very stuff of creation, developing new materials forged not for the gentle cradle of Earth, but for the relentless extremes of space. The metals and composites that build our skyscrapers and airplanes would fail catastrophically beyond our atmosphere, becoming brittle, cracking, or simply disintegrating under conditions they were never meant to endure. We must engineer a new palette of supermaterials, each one a triumph of atomic-scale design. The first enemy is radiation, a constant sleet of high-energy particles that doesn't just pass through a hull. it interacts with it, knocking atoms out of place in the crystalline structure of metals. Over time, this bombardment can turn a sturdy aluminum alloy as fragile as old porcelain, a process called radiation embrittlement. The solution may lie in nanotechnology, designing alloys with embedded nanoparticles or creating complex, self-organizing crystal structures that can absorb and dissipate this damage, healing vacancies at the atomic level before they can grow into a critical crack. Then comes the thermal assault. In space, an object in direct sunlight can soar to temperatures hot enough to boil water, while the same object in shadow plummets to hundreds of degrees below zero, colder than the surface of Pluto. This punishing cycle of expansion and contraction, repeated thousands of times, stresses materials to their breaking point. We need composites and ceramics with near-perfect thermal stability, materials whose atoms are bonded so tightly that they barely flinch as the temperature swings wildly. Some of the most promising candidates are metamaterials, substances engineered with microscopic structures that give them properties not found in nature. Imagine a ceramic tile whose surface is etched with a pattern so fine it can actively radiate heat away in one direction while insulating in another, or a polymer composite laced with microscopic capsules of liquid that burst and flow into a crack when it forms, a self-healing skin for a spacecraft. But creating these miracle materials on Earth is only half the battle. The ultimate goal is to learn to manufacture them in space itself, using the resources we find there. This is where asteroid mining transitions from speculative idea to industrial necessity. A single metallic asteroid contains more nickel, iron, and cobalt than has been mined in all of human history, along with precious platinum group metals. Instead of launching prefabricated girders from Earth at astronomical cost, we could send robotic refineries to process these raw materials in zero gravity. In the vacuum of space, we could create alloys and perfect crystals impossible to forge under Earth's gravity, building up structures layer by layer with three-dimensional printers that use concentrated sunlight as their furnace. This new material science is the bedrock of our cosmic future. It will determine the thickness of a starship's shield, the transparency of a habitat's dome, and the longevity of every bolt and seal. With these substances in hand, we unlock the potential for construction on a scale that dwarfs anything possible on our home world, allowing us to tackle the next audacious feat, building structures so vast they reshape the sky of an alien planet. These new supermaterials are not just for patching together small outposts, they are the very atoms we will use to sketch our grandest dreams against the black canvas of space. The 14th challenge asks us to shift from architecture to world building, to conceive and construct megastructures on a scale that redefines the word colossal. We are no longer talking about habitats, we are talking about crafting entire landscapes in the void, permanent homes that can support populations in the millions and industries that span solar systems. The most iconic of these visions is the O'Neill cylinder, a concept that feels plucked from the most ambitious science fiction. Picture two immense cylinders, each tens of kilometers long and several kilometers wide, rotating in opposite directions to create artificial gravity along their inner walls. Their interiors are not sterile metal corridors, but vast, terraformed valleys complete with rivers, forests, towns, and a sky created by reflected sunlight streaming in through massive windows. This is not a ship or a station, it is a sovereign piece of real estate, a new island in the sea of space. But to build it, we must first invent an entirely new discipline, orbital construction engineering. Forget cranes and cement trucks, the shipyards of the future will be silent, airless factories in high orbit, swarmed by fleets of autonomous robotic assemblers. These machines, working in coordinated swarms, would capture and process raw materials delivered by asteroid tugs, then use advanced three-dimensional printing and molecular welding to assemble the megastructure piece by colossal piece. The logistics are mind-bending, requiring the movement of millions of tons of material with pinpoint precision, all while managing the complex orbital mechanics of an object whose mass and shape are constantly changing. The structure itself demands materials that push the boundaries of physics. The primary support frames would likely need to be built from carbon nanotubes or crystalline graphene, materials hundreds of times stronger than steel yet incredibly light, to withstand the immense rotational stresses without collapsing under their own weight. Every weld, every bolt, every seam must be perfect, because a single structural failure in such a system would be a catastrophe of unimaginable scale. Yet these cylinders are just one possibility. We might also build vast solar power satellites, arrays kilometers across that collect sunlight unfiltered by any atmosphere, and beam the energy as microwaves to colonies on planets or other stations. Or we could construct orbital shipyards the size of small moons, dedicated to assembling the next generation of interstellar arcs. Each megastructure represents a leap from mere survival to true, expansive civilization in space. They are the ultimate expression of our desire not just to visit the cosmos, but to live within it permanently, to create environments that are not just safe, but beautiful, diverse, and boundless. Within those engineered valleys and under those artificial suns, society itself would evolve in new directions, giving rise to cultures, economies, and ways of life we can scarcely imagine from our earthly perspective. And to govern the growth of these new societies, we will need to engineer something equally complex and unprecedented: the social and political frameworks for a civilization scattered across the stars. The promise of limitless power whispers to us from the heart of every star. Our 15th challenge is to capture that whisper and turn it into a roar, to master the process that lights the heavens, nuclear fusion, for both our propulsion and our survival. While nuclear fission offers a practical, near-term power source for distant colonies, fusion represents the ultimate prize, the holy grail of energy science. It is the same reaction that powers our sun, fusing light atoms like hydrogen into heavier ones, releasing staggering amounts of energy in the process. The fuel for this reaction, isotopes like deuterium and tritium, can be extracted from the water ice found on moons and asteroids, offering a virtually inexhaustible supply across the solar system. The dream is a dual breakthrough: a compact fusion reactor that can provide a colony with clean, abundant power for centuries, and a fusion rocket engine that could propel a starship to a significant fraction of light speed. But between that dream and reality lies an engineering maze of almost unimaginable complexity. The core problem is one of containment. To force atomic nuclei to fuse, you must recreate conditions similar to a star's core, heating a gas into a plasma state at temperatures exceeding 100 million degrees Celsius, hotter than the center of our sun. At such temperatures, no physical container can survive contact. The plasma would vaporize any solid wall instantly, so we must build cages of pure force. The leading approach on Earth uses powerful magnetic fields in a donut-shaped device called a tokamak, which holds the superheated plasma suspended in a vacuum away from the reactor walls. These experimental reactors are monumental achievements, but they are also the size of buildings, incredibly heavy, and require more energy to start and maintain than they currently produce. For space, we need to invert that equation entirely. The challenge is to shrink this star in a bottle technology down, making it not only net energy positive, meaning it produces vastly more power than it consumes, but also lightweight, reliable, and durable enough to be trusted on a decades-long interstellar voyage or as the sole power grid of an isolated colony. Imagine the engine of a future starship. It would not have a fiery exhaust plume, but a faint, brilliant glow of energized particles. In one design, a compact fusion reactor heats a propellant like hydrogen to extreme temperatures, ejecting it from a magnetic nozzle at velocities that could reach 10% of light speed. This would cut travel times within our solar system to months and make journeys to nearby stars conceivable within a human lifetime. The engineering tolerances are almost beyond belief. The superconducting magnets that generate the containment fields must be perfect, maintaining their properties in the deep cold of space while withstanding constant bombardment from radiation. The systems that inject fuel and extract power must operate with flawless precision for years without maintenance. A single instability in the magnetic field or a microscopic impurity in the plasma could cause the reaction to quench, potentially damaging the reactor. This demands a level of material science and control system engineering that pushes the very limits of our knowledge, yet the reward justifies the centuries of struggle. A civilization powered by fusion transcends the constraints of scarcity. Energy becomes so cheap and abundant that it changes the fundamental economics of survival. On a colony, fusion power could run massive atmospheric processes to terraform a planet, energize continent-scale agricultural domes, or fuel industries that manufacture anything from spacecraft to synthetic ecosystems. It turns a precarious outpost into a thriving, growing world. For propulsion, it transforms the galaxy from a collection of isolated points of light into a network of potential destinations. Mastering fusion is more than solving an energy problem. It is about unlocking a new tier of human capability. It provides the foundational power that makes every other challenge, from recycling to megastructure construction, immeasurably more achievable. With the raw power of a star at our command, we shift from merely adapting to the harshness of space to actively reshaping it to our needs. This godlike control over energy and motion, however, brings with it a profound new responsibility, one that extends far beyond the lifetime of any individual engineer or colonist. The power of a star is meaningless if the machine that channels it cannot survive its own journey. This truth leads us to the 16th Great Challenge, a silent discipline that underpins every other system, ensuring long-term reliability and redundancy across decades of absolute isolation. An interstellar arc or a Martian city has no supply chain, no emergency hotline, and no possibility of a rescue mission. A single failed valve, a corrupted data chip, or a fatigued structural beam could cascade into catastrophe with no outside intervention possible. Therefore, we must abandon the very idea of maintenance as we know it and engineer a new philosophy of permanence, creating systems that are not merely durable, but inherently resilient and self-sustaining. This begins with a radical embrace of redundancy, but of a specific kind. It is not enough to have two of every pump that merely doubles the number of parts that can fail. Instead, we need systems designed for graceful degradation. Imagine a starship's power grid. If one solar array or reactor module fails, the network should automatically reroute energy, perhaps by dimming non-essential lights and prioritizing life support, allowing the colony to continue functioning at a reduced capacity indefinitely. The system doesn't crash, it adapts, like a living organism redirecting blood flow from a minor injury. To achieve this, every critical component must be imbued with a level of self-awareness we've never demanded from machinery. Advanced sensors will monitor not just temperature and pressure, but microscopic signs of wear, vibration patterns that hint at impending bearing failure, or subtle chemical changes in lubricants. This constant stream of data feeds into predictive maintenance algorithms, artificial intelligences that learn the unique heartbeat of their machine and can forecast a breakdown months or even years before it happens. But prediction is only half the solution. The true breakthrough lies in the response. This is where the colony's infrastructure must become a closed loop of creation and repair. Onboard three-dimensional printers, fed by raw materials recycled from worn-out parts or mined from local asteroids, could fabricate a replacement component on demand. The vision extends further to the realm of nanotechnology, where swarms of microscopic machines could be deployed to perform repairs at the molecular level, sealing micro-cracks in a pressure hull or clearing blockages in capillary fluid systems too small for any tool to reach. The ultimate goal is to design a form of mechanical biology where our machines possess a primitive kind of healing. A composite material might be laced with microcapsules that release a healing agent when stressed, or a circuit board could have redundant pathways that activate when the primary one is damaged by radiation. This relentless focus on resilience extends to the most precious cargo of all, information. The colony's entire cultural, scientific, and genetic database must be preserved against cosmic rays, mechanical failure, and the simple erosion of time. We might store this knowledge in multiple formats, etched into durable sapphire disks, encoded in synthetic DNA strands which are incredibly dense and stable, and broadcast redundantly across the interstellar network. The archive itself would need to be self-verifying, constantly checking for data corruption and repairing itself from backup copies. This 16th challenge is ultimately about engineering trust, building systems so fundamentally reliable that human lives can be entrusted to them for generations. It transforms our machines from tools into stewards, silent guardians that watch over the continuity of life and knowledge in the void. Yet, to truly secure that continuity for the centuries-long voyages between stars, we must confront a biological limit more fixed than any machine's, the human lifespan itself. A civilization is defined by what it remembers, on a voyage spanning centuries or in a colony severed from Earth by light years. The continuity of knowledge becomes the most critical life support system of all. The 17th challenge is the preservation of our collective memory, an engineering puzzle that merges data storage with the very soul of a society. We must design archives that are not just libraries but indestructible time capsules, capable of safeguarding every technical manual, every piece of art, every historical record, and every strand of genetic code against the relentless decay of deep time. Cosmic rays pose a silent, constant threat, flipping bits in digital memory in a process called bit rot, where files gradually corrupt into digital ghosts. The solution is a multi-layered fortress of information. Critical data would be encoded with sophisticated error-correcting algorithms, the same mathematics that allow a scratched DVD to play perfectly, but scaled to cosmic extremes. The storage media themselves must be physically robust, perhaps etched onto plates of synthetic sapphire that can withstand radiation and temperature swings for millennia, or encoded into the stable backbone of synthetic DNA, where a single gram can hold the entire text of the internet. And we would never keep just one copy. Redundant archives would be placed in geographically separate vaults, buried deep within a colony's bedrock or launched into stable orbits, a distributed backup for an entire civilization's identity. Yet a book locked in a vault teaches no one. The harder task is engineering the living transmission of that knowledge across generations who have never seen Earth. This is where information systems must become educational and cultural engines. Imagine a child born on a starship, their entire world a metal cylinder. Their education would be guided by immersive artificial intelligence tutors, patient digital mentors that adapt to each learner, using virtual reality to demonstrate the principles of stellar navigation or the ecology of a rainforest they have never walked. But technical knowledge alone creates a society of skilled mechanics, not a culture. We must also architect the rituals and experiences that pass on why they are on this journey. Curated cultural archives could allow generations to experience the symphonies of Beethoven, the plays of Shakespeare, or the natural wonders of Earth as immersive virtual experiences, not as historical footnotes. Annual observances might recount the stories of the founders, the moment of launch, and the original mission statement, weaving a shared narrative that binds the community together. This active cultural engineering prevents the unthinkable, a form of societal amnesia known as technological backsliding, where a colony forgets how to repair its own fusion reactor or loses the meaning behind its own laws. The goal is to build a society that remembers not only how to fix a water reclaimer, but the philosophical ideals that prompted their ancestors to venture into the dark. This living library of technical skill and cultural memory is the software that runs a durable civilization, ensuring that the purpose of the journey burns as brightly for the 10th generation as it did for the first. And that purpose, the driving curiosity to explore, will inevitably lead them toward the greatest unknown of all, the possibility that they are not alone in their journey through the silent sea of stars. The silent frontier holds more than just emptiness, it holds the potential for the utterly unexpected. Our 18th challenge is to engineer not just for the dangers we can name, but for the mysteries we cannot yet conceive, preparing our vessels and our protocols for the possibility of first contact or unknown cosmic phenomena. While this sounds like the realm of science fiction, it is a serious engineering imperative for any civilization venturing into the deep unknown. The core principle is cautious flexibility, building systems that can observe, analyze, and respond to the unprecedented without panic or catastrophic failure. This begins with the eyes and ears of the starship. Scientific sensor packages cannot be designed only to confirm what we already know. They must be built with broad-spectrum sensitivity to detect anomalies. Imagine a suite of instruments that monitors not just known radiation bands, but the entire electromagnetic spectrum for structured patterns or unexplained energy fluctuations. It would include gravitational wave detectors attuned to subtle ripples, and particle collectors designed to capture and analyze matter with atomic structures unlike anything in our periodic table. The artificial intelligence governing these sensors must be programmed not to discard outliers as noise, but to flag them for intense scrutiny, asking a simple, profound question: does this pattern have a signature that suggests something other than natural chaos? But detection is only the first step. The greater challenge is engineering layers of safeguards, both physical and digital, to protect against unforeseen hazards. A starship might encounter a region of space with a novel form of radiation that penetrates standard shielding, or drift through a cloud of exotic matter that interacts unpredictably with the hull. Our engineering response must be multi-layered. Physically, we might design modular shield sections that can be reconfigured or augmented in response to sensor data, or maintain a sterile, isolated laboratory module for the remote analysis of any potentially hazardous samples, treating the unknown with the utmost respect. Cybernetic safeguards are equally critical. The ship's central computer, the brain of the entire mission, must be insulated from potential external manipulation or corruption. This could involve air-gapped backup systems, decision protocols that require multiple layers of human and artificial intelligence consensus before altering course or opening a communication channel, and rigorous psychological training for the crew to maintain rationality in the face of the profoundly strange. The goal is not to build a fortress of fear, but a vessel of wise curiosity. We are engineering the capability to say hello to the universe while always keeping a prudent hand near the airlock controls. This mindset of prepared wonder, of designing for discovery while prioritizing preservation, becomes the essential philosophy that must guide the final and greatest task of all, weaving every one of these monumental solutions into a single, living, breathing whole. A starship is not a collection of parts, but a single, breathing organism. The 19th and perhaps most profound challenge is the art of weaving every monumental system we have discussed into a seamless, synergistic whole. None of these puzzles exist in isolation. They are threads in an impossibly complex tapestry, where pulling one thread tightens or loosens a dozen others. Your revolutionary fusion propulsion engine does not just provide thrust, it generates immense heat that must be managed as a resource for the habitat. Its radiation output influences shield design, and its voracious appetite for fuel dictates the entire logistics chain of the mission. The shape of your radiation shield defines the internal architecture of the living quarters, which in turn determines the layout of your life support plumbing and agricultural modules. Every engineering decision echoes through the entire vessel, creating a cascade of consequences that can mean the difference between a graceful voyage and a silent tomb. This forces a complete reinvention of the design process itself. We can no longer afford to have teams of specialists perfect their components in isolation, then hope they fit together at the end. The starship must be conceived from the very first sketch as a holistic, symbiotic entity. This demands a new kind of engineer, the ultimate systems thinker, whose expertise lies not in a single field, but in understanding the intricate dance between physics, biology, chemistry, and human psychology. Their primary tools will be vast, multi-layered computer simulations, digital twins of the entire spacecraft that run for years in virtual space. These models won't just test if a bolt fits, they will simulate the subtle interplay of 1,000 systems over a century of flight. They will ask questions we might not think to ask. What happens to the microbial balance in the water recyclers during a prolonged period of high G acceleration? How does the psychological stress of a meteoroid impact alarm affect crew decision-making in the agricultural bay 12 hours later? The simulation becomes a crystal ball, revealing failure modes born from unexpected interactions long before any metal is cut. The goal of this holistic design is to create a closed-loop technological ecosystem where the very concept of waste is engineered away. The heat from the reactor powers the water purification system. The carbon dioxide exhaled by the crew is not a toxin to be removed, but a precious feedstock for the algae farms. The inedible plant matter from those farms becomes raw material for the three-dimensional printers that fabricate replacement parts. Even the crew's psychological need for variety could be met by virtual reality systems powered by the excess computational cycles of the navigation computer. This is engineering as a form of natural law, creating a vessel that doesn't just carry life, but embodies the elegant, efficient cycles of a living world. Success in this grand integration is the final and most difficult step, the moment when 20 impossible challenges cease to be individual problems and fuse into a single, audacious solution, a working blueprint for humanity's future among the stars. A blueprint is worthless without the means to build it. This final, overarching challenge is not about physics or biology, but about the architecture of collective will, the economic and logistical framework to make interstellar dreams tangible. The sheer scale of resources required to construct even a single-generation ship or a permanent lunar colony dwarfs the gross domestic product of most nations on Earth. We cannot simply wish these projects into existence. We must engineer the societal machinery to fund, organize, and supply them across timelines longer than a human career. This is the meta-engineering of civilization itself, a puzzle that ties our earthly present to our stellar future. The first hurdle is collaboration. No single government or private entity can or should shoulder this burden alone. It demands a new model of partnership, perhaps a consortium resembling a global space agency, but with the agility of a private venture, blending international scientific talent with industrial-scale execution. This entity would need a stability that transcends political cycles, operating on century-long plans with funding locked in by treaties and multi-generational trust. Imagine a project whose groundbreaking ceremony is attended by great-grandchildren of the original architects, a testament to human patience and shared purpose. Funding mechanisms must be equally revolutionary. Traditional return on investment models break down when the payoff is 100 years away. We might see the creation of interstellar bonds, long-term financial instruments backed by the future value of off-world industries, or a global fund supported by a tiny fraction of transactions in a digital economy. The capital required is astronomical, but so is the potential yield, not in immediate profit, but in the survival and expansion of our species. This leads to the engine that could power it all, a self-sustaining space-based economy. The initial colossal investment from Earth must seed industries that then generate their own value, creating a virtuous cycle. Two possibilities stand out. Space-based solar power involves constructing vast arrays in orbit that capture sunlight unfiltered by atmosphere and beam clean energy to Earth via microwaves, providing a nearly limitless resource that could fund further expansion. Asteroid mining is the other pillar, where robotic fleets extract precious metals, water, and rare minerals from nearby space rocks, supplying raw materials for orbital construction and eliminating the need to launch everything from Earth's deep gravity well. These industries would birth the first true off-world supply chains, a logistics network stretching from fabrication plants in low Earth orbit to refineries on the Moon to construction docks at Lagrange points. It is an economy born in the void, trading in kilowatts beamed across space and platinum mined from captured asteroids. This 20th challenge, therefore, is the keystone that locks all the others into place. It answers the most practical question of all: who pays for it and how? By architecting this sustainable economic engine, we transform the dream from a drawing on a page to a project on a docket. It is the final, decisive step that proves we are not just dreamers of the stars, but builders ready to begin. This intricate web of challenges reveals a deeper truth about our cosmic ambition. Each solution is not an isolated breakthrough, but a key that turns a lock in a dozen other doors. The relationship between propulsion and radiation shielding is a perfect example. A revolutionary engine that achieves high speeds with less propellant mass directly eases the punishing trade-off for shield weight. Suddenly, protecting the crew becomes more feasible because you are not fighting physics to move the very armor meant to save them. This synergy ripples outward. The sophisticated artificial intelligence required to pilot a starship is the same intelligence that can manage a swarm of autonomous robots mining ice on a distant moon or orchestrating the three-dimensional printing of a habitat dome. A breakthrough in metamaterials, born from the need to withstand interstellar dust impacts, could also yield substances that self-regulate temperature in a Martian greenhouse or form the ultralight skeleton of an orbital megastructure. This interconnectedness transforms the monumental task from a linear checklist into a dynamic ecosystem of innovation. Progress in one discipline doesn't just add a piece to the puzzle, it reshapes the edges of all the surrounding pieces, making them easier to fit. This creates a powerful positive feedback loop, where each solved challenge lowers the barrier for the next, accelerating our capabilities in a way that linear thinking cannot predict. The journey to live among the stars, therefore, is far more than a destination. It is the ultimate catalyst, a forcing function that pushes every field of human knowledge, from quantum physics to synthetic biology, to its absolute outer limits. The technologies we invent to recycle every drop of water on a generation ship could lead to closed-loop systems that eliminate scarcity in Earth's most arid regions. The medical advances to combat cosmic radiation might unlock new understandings of cellular repair, revolutionizing healthcare. the compact fusion reactors that power our stars could one day provide clean, abundant energy for our home planet, ending our reliance on fossil fuels. In striving for the stars, we are not abandoning Earth, we are building a brighter future for it. The greatest legacy of this grand endeavor may not be the colonies we found among alien suns, but the cascade of wisdom and tools we create along the way, proving that to reach for the heavens is to lift up our entire world. These 20 mountains stand before us not as walls but as invitations. The path to living among the stars is paved with these monumental engineering challenges, each one demanding a fundamental reimagining of what is possible. From the physics that bends space to the psychology that binds a community, they ask us to rebuild civilization from first principles, atom by atom and law by law. We must learn to sail on beams of light, to forge ecosystems in metal cans, and to design societies meant to endure for centuries in the dark. It is a blueprint for nothing less than human evolution itself. And while the scale can feel overwhelming, history offers a quiet, powerful reminder. Every civilization-defining leap, from crossing oceans to splitting the atom, began as an impossible dream scribbled on the edge of understanding. The cathedrals, the space stations, the global networks, all were once considered fantasies that defied the resources and the will of their age. Our journey to the stars is no different. It is the next chapter in that same story of stubborn curiosity. The critical insight is that these 20 challenges are not isolated impossibilities. They are a web of interconnected puzzles where a solution in one discipline becomes a key for another. Mastering compact fusion solves both power and propulsion. Advances in self-healing materials make long-term reliability achievable. Each breakthrough creates a ripple, lowering the barrier for the next, accelerating our capabilities in ways we cannot yet predict. This interconnectedness transforms a daunting checklist into a dynamic ecosystem of innovation. By tackling them systematically with patience and global cooperation, we are charting a course for more than mere survival. We are designing a future of growth, of abundance, and of profound new understanding. The stars represent the ultimate frontier, a call to expand the sphere of human experience and responsibility. Answering that call is perhaps our generation's greatest undertaking. It will require a fusion of minds across every continent, a commitment to relentless innovation that spans lifetimes, and an unwavering vision held steady across decades. The journey does not begin with a single, fiery launch. It begins in laboratories and workshops, in simulation software and policy forums, with the collective will to solve these 20 great puzzles. It begins with us, so we turn the question to you as fellow architects of tomorrow. Which of these challenges do you find most daunting or, conversely, most inspiring? Is it the sheer physics of starflight or the delicate art of crafting a closed-world ecology? Share your thoughts in the comments below. This conversation is the very first step in that collective effort. If you want to join more deep dives into the frontiers shaping our future, be sure to subscribe. And as you look up at the night sky, remember this final, essential truth. The future is not a distant place we are passively traveling toward. It is a reality we are actively building together with every question we ask and every problem we dare to solve.